period. Be very careful about this. I'm going to show you in a minute about this, using that 2 pi over b as the period, the b is the period, for tangents and cotangents. It doesn't quite work there, and I'll show you why in a few minutes, okay? So, next part, graph the function, what's the period of each function? So let's take a look here. For this function, the first one, we can start by graphing real briefly a sine of x. So sine of x, we looked at that a few minutes ago, it starts at 0, goes up and down and repeats one cycle over a period of 2 pi. So make sure you know how to draw this. This would be pi over 2, this is 0. So it looks something like that, and then it would continue on this way as well. Okay, so something like that, and it continues on going this way. Now, what we have here is we have this pi over 3. This pi over 3, remember, that is changing the period. It's like a horizontal stretch or compression. It's a number being multiplied right onto that x value. So this one is f of x equals sine of x. And then what we need to do is do f of x equals, we need to do f of x equals, or maybe not f of x, let's make that g of x equals sine of pi over 3 times x. So this is going to be some sort of a horizontal stretch or compress. And we can get this pretty easily. We know that the number that's right there is supposed to be 2 pi over b, the period. But we know that that number right there is actually pi over 3. So we just set that equal to it like that, and we solve for b. So to solve for b, we can multiply both sides by b, and we get 2 pi equals pi over 3 times b. We can cancel out the pi's, and then we can multiply both sides by 3. And we'll get that b equals 6. So what that means is I come in here, and I'm going to redraw my graph. I should have put that over here, but I'm going to redraw it over here just because the period is 6. And I'll go with something like 3, 6 here, 6 out here. And then my graph is just going to do this, something like that, and continue on like that. Here's -3, and so on and so forth. This is the g of x. I should have put this over here. This is the g of x equals sine of pi over 3 times x. Okay? Now take a look at this next one. This is cotangent. Now, when we look at the tangent function, this is how I'm going to go about graphing this. Whoa, what happened here? Okay, sorry about that. Not sure why that happened, but anyway, we look at the tangent function, and the tangent function looks like this with our asymptotes, right? And the asymptotes are occurring every distance of pi. So this is negative pi over 2. This one is at pi over 2 because it has a period of pi. And so it does that. Now, how do we get the cotangent graph from this? So this is tangent x. Cotangent, we do the reciprocal graph, which means we take everything that's a 0 here at 0. This is at pi. So at 0, at pi, those zeros, and over here at negative pi, those become asymptotes. Zeros become asymptotes. So this will be an asymptote, this will be an asymptote, this will be an asymptote. And asymptotes become zeros. So we have a 0 at negative pi over 2, so this will be a 0. A 0 at pi over 2, that'll be a 0. We'll have another 0 over here. And so those become our zeros. And then everything that's big, it's big near pi over 2, becomes small. But it has to stay positive on that same side. So on this side, between 0 and pi over 2, it's positive there. So on this side, it has to be positive in this area. And we notice that as we get closer to 0, these numbers become smaller. And so it's going to go the opposite way. Near 0, it's going to get big instead of becoming small. Over here, in this little zone here, it's getting small here and going to 0 there. So we're going to end up making it go like this. Okay? And so you can just kind of repeat this around, and this will be your cotangent graph. All right, there's cotangent of x. That's what that graph looks like. Now what they're asking us to do is do cotangent of 2t. Now, if we were to assume that this 2 right here, if we did 2 equals 2 pi over b, we would get 2b equals 2 pi, and we would get b equals pi, right? Well, a period of pi is what the period is for regular old cotangent, okay? But what we're doing is a horizontally stretched or compressed, actually compressed since it's 2, it's greater than 1, it's going to horizontally shrink it by 2, which means we should actually get half of the period that we had for cotangent graph. We should get half of it. So if I go to graph this, what actually happens is I get this whole thing compressed. All right, I still have my asymptote here at 0, but then instead of at pi, it's at pi over 2. That's where my asymptote gets compressed to, and negative pi over 2. Those are my asymptotes now. And so my graph gets squished down like this. And so had I just looked at that equation for the sine and cosine and just used that, it would have told me, and I would have thought, oh, the period is just pi. But that's wrong. You can't use that for cotangent and tangent. That only works for sine and cosine. And so, and secant and cosine, I guess, is going to work there. But it's only going to work, it's not going to work here. We actually have to have half of that. And so here, b is pi over 2, half of it. All right, because it's that compressed version. Because you got to remember, tangent and cotangents always have, they have half the period that sine and cosine do. All right. Trigonometric identities. Let's talk about some of the common identities. So first real common one is Pythagorean theorem. X squared plus y squared equals 1. And we know that the x values are cosine, so this can be cosine squared. And that the sine y values are sine, so this is sine squared. And it's going to equal 1. And that's going to always be true, right? The Pythagorean identity, cosine squared plus sine squared equals 1. I'll derive the other two for you here outside of the notes, but I'm not going to do it right now for you. But suffice it to say, these are the Pythagorean identities. These bottom two just come from the first one pretty easily. And again, take a look at it in the notes and you'll see, because I'll go back and complete it. But it's right there. Okay, these three you are totally expected to know. They're some of the most commonly used ones. Make sure you have them memorized. If you just can remember the Pythagorean identity, as long as you can remember this right there, you should be able to come up with that, and then come back and look at the notes, and you'll see how I come up with the other two really quickly from that one. It just is a matter of a quick division of either dividing by cosines or dividing by sine. All right, so applications of identities. Here's next. Here what we have are the addition formulas, where if we have something like this, we can actually rewrite it. And so here we have cosine of pi plus cosine of x. So that goes along with this one right here, a plus b, which means we can call this a, this b, and we can rewrite this with what's written right there. And so we can write cosine of a, which is pi, times cosine of b, which is x, minus sine of a, which is pi, times sine of b, which is x. All right, and there you go. And this can be useful sometimes if you need to split something up inside of trigonometric functions, like you can't do something with it. And in fact, let's look at an example right here where we can do this. Now here we have the sine of 5 pi over 12. Well, 5 pi over 12 is not one of the common ones we know from the unit circle. If we look at our unit circle, if I just look at this little quadrant of it right here, what do we have? We have pi over 6, we have pi over 4, and we have pi over 3. None of those are pi over 12s, okay? But if we change their denominators, right, I can make this one 4 pi over 12, and I can make this one 3 pi over 12, and I can make this one 2 pi over 12. And if there's some way I can add or subtract two of these together to get me a 5 pi over 12, then I'll have a way to do it. So, for example, if I add 3 pi over 12 and 2 pi over 12, right? 3 pi over 12 plus 2 pi over 12, that equals 5 pi over 12, which is exactly what we have right there, which means I can rewrite sine of 5 pi over 12 as sine of 3 pi over 12 plus 2 pi over 12, okay? And by doing that, what that does is it allows me to use this, right? We were doing sine, right? I can use this one right here, sine A cosine B plus cosine A sine B, and actually figure out what this is. So I can write this as sine of 3 pi over 12 times cosine of 2 pi over 12 plus, right, am I doing this right? Cosine, yep, cosine of 3 pi over 12 times sine of 2 pi over 12. I can write it like that, you see? And then these actually reduce. Remember, 3 pi over 12 is just pi over 4. So this is sine of pi over 4. This is cosine of pi over 6. This is cosine of pi over 4. And this is sine of pi over 6. And now that I have that, I should know pretty nicely from my unit circle that the coordinates here are square root of 2 over 2, square root of 2 over 2. And right here, it's square root of 3 over 2. Sorry, I started to say 1/2. And then 1/2. And so the sine of pi over 4 is just this value right there. It's a square root of 2 over 2. The cosine of pi over 6 is this value right there. It's square root of 3 over 2. And then cosine of pi over 4 is going to be this square root of 2 over 2 right there. And sine of pi over 6 is this 1/2. So times 1/2. And then I can start multiplying all this together and figuring this out. So this is going to be square root of 6 over 4 plus square root of 2 over 4, which just gives me square root of 6 plus square root of 2 over 4. Okay? So you can go through and take something that wasn't on the unit circle, if it works out nicely, and turn it into values that are on the unit circle, and that can help you a lot sometimes. Next one is the half angle formulas. Here, what this allows you to do is take something that has a square in it and reduce it down to something that doesn't have a square in it. So here we have sine squared theta equals 3/4. Well, what we can do is actually replace that sine squared, right? We can replace it right here with this, all right? See that? And so what we can do is write this as 1 minus cosine of 2 theta over 2 equals 3/4. And then I can multiply both sides by 2, and I get 1 minus cosine of 2 theta equals 6/4, which reduces to 3/2. And then I can say, all right, I can add cosine of 2 theta to both sides, subtract the 3/2, and I can get ultimately that cosine of 2 theta is equal to 1 minus 3/2. And 1 minus 3/2 is negative 1/2. And so I've got that right there. And so just for a moment, I'm going to say something like, just to make it easier to see, I'm going to say let phi equal 2 theta. And then what I have is cosine of phi equals negative 1/2. And where does that happen? Where do I get a cosine is negative 1/2? Well, if I look at my unit circle real quick, my negative 1/2's on x, this is negative 1/2 back here. And that's going to give me two places, here and here. So one of them is going to be there, one's going to be there. This is going to be at 3 pi over 4, or 3 pi over 2. And then this is 4 pi over 2, and this is 5 pi. Wait, that's, oh, no, I'm doing the wrong thing. Not pi's over 2's. My mistake. Don't write that. This is at pi over 3's. So this is 2 pi over 3, and this is at 2 pi over 3 pi over 4 pi over 3. Okay, and so our coordinates here are negative 1/2 and square root of 3 over 2, and our coordinates down here are negative 1/2, negative square root of 3 over 2. So both of those work for phi. So that means that phi has to equal 2 pi over 3 or 4 pi over 3. But remember, phi is 2 theta. Okay, so that means that we can set this up as 2 theta equals 2 pi over 3, which will give us that theta equals pi over 3. And we can set this other one up as 2 theta equals 4 pi over 3, which just gives us theta equals 2 pi over 3. All right, so that gives us our two answers. And you think, okay, now we're done. We've got this point here, and we've got this other point right there. Those are our two values. Now, you have to be a little bit careful because sine squared of theta equaled 3/4, and that means that sine of theta equals plus or minus the square root of 3/4. But 3/4, not a fifth, 3/4. And that also means then that sine squared theta equaling 1 minus cosine 2 theta over 2 means that sine of theta equals plus or minus the square root of 1 minus cosine 2 theta over 2. Which means that we have to worry about plus or minuses. So if we look at something like sine equals the plus or minus 3/4, where when we square it we get 3/4. Well, sorry. Well, you have to be careful of that, because if we square negative 3 pi over 2, right? Because sine is the 3 pi over 2 part, so that gave us these 2 points. But if we square negative 3 pi over 2, we also get 3/4. So we not only have to use the pi over 3's, we have to also do the plus or minus of each of them. Okay, and then that is our actual answers. So we end up with that. We end up with all these points basically. They all work for it. So be careful with that when you're dealing with pluses or minuses. Here's a double angle formula. Find all solutions on this interval of this equation. I'm going to write this out in the notes for you to look at. Just you can give it a try yourself, and then I'm going to go ahead and do it. But basically, you're going to use this right here and go through and do it. So again, you need to be able to use these, but I'm going to do it in the notes because this video is getting pretty long here. But take a look at it in the notes, see it worked out. Try it yourself, see it worked out. Over here, law of cosines, you need to know this one, right? It's basically like the Pythagorean theorem. You notice you can see the Pythagorean theorem right here at the very beginning of it. There's a Pythagorean theorem with this little correction for it being not a right triangle. So, Pythagorean theorem here, and then this little correction added on at the end because it's not a right triangle. Essentially, this is like Pythagorean theorem for all triangles. And if it is a right triangle, then this theta becomes the cosine of 90, which is 0, and so this whole last part just disappears, and it's the pure Pythagorean theorem. I'm not going to go through deriving it here. If you're really super interested in seeing a derivation of it, because there's multiple ones, then let me know and I'll come up with something for you and show you. But suffice it to say, you should know that one and be familiar with it, the law of cosines. Over here, you have a law of sines. And basically this law of sines, I'm going to write it in here for you, is that sine of an angle divided by the side across from it is equal to the sine of any other angle divided by the sine of the side across from it. And then, these should be lowercase a's and b's for this, sorry, a, b, and it can equal the third sine of the third angle divided by the side across from it. So if I draw some arbitrary triangle, and if I make this alpha, this would be side A. If this is angle beta, This would be side B. If this is angle phi, going to learn a lot of Greek letters in math. This is going to be angle C. And so if this is the way your triangle is set up, then the sine of this angle to the side across from it is equal to the same ratio for any other angle, sine of any other angle, and the side across from it. So that's a good one to help you know. So if you go through and I just wrote on the last page, so here on this page, we could actually use it to solve this. So a triangle has a side C. So let's just draw some triangle here. We have a side C, which is equal to 2. We'll call this 2, which makes this angle phi. It has an angle A. Where's A? So let's make this angle A right here. We'll make this pi over 4. And then this is going to be side A, and this will be angle B, which is pi over 3, and this will be side B. And so if this is the case, it says find the length A of the side opposite A. So what we're trying to do is find, oops, I thought I had it on highlighter. We're trying to find this one right there, okay? And so we could do this, we can set this up and go through and try and solve it. So what we've got is we've got to basically set up our ratio. So if we set this up, we can do, what can we do here? We can do, we can go ahead and find what phi equals first. That's the first thing I need to do. And we can do this because we know that all the sides of a triangle have to add up to 180 degrees, or all the angles of a triangle have to add up to 180. Well, we don't have 180, we have this in radians, and 180 degrees is pi radians. So we need all three sides to add up to pi radians, which means that pi over 3 plus pi over 4 plus phi has to equal pi. And so phi is going to equal pi minus pi over 3 minus pi over 4. And that's just going to be 12 pi over 12 minus 4 pi over 12 minus 3 pi over 12. And so that's going to be 5 pi over 12. That's phi. So now we know phi is 5 pi over 12. Okay? And then we can set up our ratio. We can do the sine of 5 pi over 12 divided by the side across from it, the 2. So this divided by that. And we're going to make that equal to the sine of pi over 4 divided by the side A across from it, which is what we want. I can take the reciprocal of both sides. Sine of 5 pi over 12 is A over sine of pi over 4, just to get that A out of the denominator. And we get A equals 2 times the sine of pi over 4 divided by the sine of 5 pi over 12. And I think we just did the sine of 5 pi over 12 a few pages back, didn't we? Is that the one we did? Yep. So if we go back a few pages, we see, where is it? The sine of 5 pi over 12 ended up just equaling this right here. I'm just going to copy it over. 5 pi over 12, right? So come over here, and we've got that is what that equals. And so this is sine of 5 pi over 12, and that's what that equals. And sine of pi over 4, you should be able to do just from the regular old unit circle. So go ahead and give that a try. Plug those in and see if you get the answer. Ultimately, I believe I got that. What did I get? Well, I'll write it out for you in the notes here, and you can take a look. I'll put the final answer in, but you basically should be able to get that one right there. Okay, so plug this in for the 5 pi over 12, sine of pi over 4, get from the unit circle, plug them all in, get your answer, and I'll have it for you written in the notes after you try finishing it off. Okay, that's it for this section. Thank you.